guys. This is lesson 1.3, the first half. It's all about electron configurations and periodic trends. Our objectives today are to write electron configurations and draw orbital diagrams for atoms, and then explain the significance of something called the exclusion principle and Hund's rule. So take a look at this energy diagram. So this shows us the difference in energy levels for hydrogen orbitals. For hydrogen, all orbitals that have the same value for n have the same energy. Hydrogen's only electron is in its lowest state, the most stable state, when it's in the 1s orbital. When that electron is excited, it might be found in any of the other orbitals, depending on how much energy is reserved. Okay, this little diagram might be a little hard to interpret. Let's take a look. So remember everything we learned in the last lesson. This first little box is meant to represent the 1s orbital. That means that n is equal to 1 and L is equal to 0 here. The 1s. This here would be our 2s orbital, where n is equal to 2 and L is equal to 0. Then I've got three more boxes. These would be the orbitals for where n is equal to 2 and L is equal to -1, 0, and +1. That would mean there's three possible combinations. N is equal to 2 and L is equal to -1. N is equal to 2 and L is equal to 0. N is equal to 2 and L is equal to 1. We would call these all 2p orbitals, but they'd be in different orientations, X, Y, and Z. But notice that for hydrogen here, whether it's 2p or 2s, those orbitals are exactly the same energy level. So if I have an electron, hydrogen, and it's hanging out in its 1s orbital, then it absorbs some energy and it gets bumped up to a higher orbital. Well, the 2s and the 2p are at exactly the same energy level. There's no difference in energy between 2s and 2p. That is not the case for other um, for other elements. Hold on a second. I have to figure out how to change screens. How do I turn off my pen? So for atoms that have two or more electrons, their orbitals have similar shapes to hydrogen, but the interactions between those electrons result in orbitals that, even though they have the same value of n, are at slightly different energy levels. For before, when I had the orbitals for hydrogen, remember that they were the 2s and the 2p orbitals were exactly the same level. That's not the case if there's extra electrons kicking around. Now my 2s and 2p orbitals are at just slightly different energy levels. It's a result of interactions between the electrons in those same uh, with the same values of n. So this is 2s and this is 2p, but 2p is at a slightly higher energy level than 2s. You can imagine that it would take just a little bit more energy to excite an electron from 1s to 2p than it would to excite an electron from 1s to 2s. Since low energy typically means stability, it's reasonable that the most stable energy state, the ground state, for any atom is one in which the electrons are in the lowest possible energy level. We want those electrons at their most stable state to be in the lowest possible orbital. But we can't just jam into all the electrons into the lowest orbital, into the 1s orbital. Remember that all of these electrons have a negative charge. They're repulsed by one another. You can't just jam them all into the same space. In order to understand what's going on and why we can fit some electrons into the same orbital and not others, we need to learn about the fourth quantum number. So we've learned about three quantum numbers. N tells us about size, L tells us about shape, M1 tells us about orientation, but this fourth quantum number is the spin quantum number, and it describes the electron's spin. Electrons can spin in one of two directions. Each of them generates an electric field, and we say that the two possible values are positive one half or negative one half. It's like imagining you can have two electrons that spin clockwise or counterclockwise. And because they're spinning in opposite directions, you can end up with two electrons in the same orbital. The Pauli exclusion principle tells us that only two electrons of opposite spin can occupy. That's why orbitals can have a maximum of two electrons. So the Pauli exclusion principle tells us we can only have two electrons in the same orbital, and they need to be spinning in opposite. No two electrons in an atom can have the same four quantum numbers. Okay, let's take a look at what this means as soon as I can find my pen. So the possible quantum numbers for hydrogen. Well, hydrogen only has one electron. So its quantum number would be n equals 1 and L equals 0, M1, 0, and MS would be, we start by convention with positive one half as the first value for MS. Let's take a look at helium. Helium, its first electron is going to have exactly the same quantum numbers as hydrogen's first electron. N equals 1, L equals 0, M1 equals 0, and MS equals positive one half. Okay, but now things change. Now I've got a second electron for helium. It can't have exactly the same quantum numbers, so let's see what changes. Here, N would still equal 1, L still equals 0, M1 still equals 0, but in order to have different quantum numbers than the first electron, MS, the spin quantum number, has to be negative one half. By convention, we start with the positive one, then we go to the negative one. But they're just representations. You can imagine this being like clockwise and this being counterclockwise. Okay, so now I've got one electron in 1s spinning one direction and the other electron in 1s spinning in the opposite. For lithium, the same thing would happen. That first electron would need to be in the lowest possible energy configuration. So N equals 1, L equals 0, M1 equals 0, and MS equals positive one half. The second electron would need to be in the second possible lowest energy state. So N equals 1, L equals 0, M1 equals 0, and MS equals negative one half. Okay, now things change again. Now I've got all of the n equals 1 possibilities full of electrons. I can't add a third spin. I can't change anything else based on what my possible values for electron number or orbital numbers are. So my third electron needs to go into a higher energy level. That would be when n equals 2. Here again, the lowest possible value for this would be L equals 0. Remember that when n equals 2, you've got 3 possibilities for L. So remember that for when n equals 2, And there are three possibilities for L. L can be -1, 0, and 1. The 0 is actually the lowest energy configuration. So L equals 0. That would be, remember, the same as 2s. And M1 equals 0, and MS equals positive 1/2. I'm hoping that you're starting to see the pattern here. We're always going to fill the lowest energy shells for everything first. But this is a bit tedious. We could keep going this way, but once we get to things like uranium, we've got a lot of quantum numbers to write out. Having a short form for this is really, really helpful. So let's talk about that. Let's talk about how we end up with some kind of shorthand. But before we do that, there's some things to remember. Remember that orbitals don't really electrons don't really fill orbitals like they're some kind of empty container. Orbitals aren't little boxes that hold electrons. Electrons don't really fill orbitals one at a time. Orbitals don't really have a substance or shape. They're just useful equations, um, probability, prediction of where that electron can be. But super convenient to use this model, like orbitals are little boxes that get filled with electrons. So that's what we're going to do. We're going to talk about them like they are little shells can be filled with electrons, but in reality, that's not quite what's going on. Okay, so take a look at what we've got here. Here we've got the atomic orbitals and their relative energy levels. This first one, think about this is when n equals 1. Here, these two are when n equals 2. This is when n equals 3. So we can take a look at these and give them some labels. This here is the lowest energy level, n is equal to 1, so we call it 1. In this configuration, then we know if n is equal to 1, L has to be equal to 0. That's S. This is the 1s orbital. The next one is when n is equal to 2 and L is equal to 0. Again, when L is equal to 0, that's S. So that's 2s orbital. Remember that each of these orbitals can have 2 electrons in them, spinning in opposite directions. Then over here, these two are both when n is equal to 2. But here we've got L equal to negative, or L equal to 1. So M1 can equal -1, 1, 0. So these are the two p orbitals. There's 3 of them. This would be X, Y, and Z. 3 different orientations. Remember that each of these can have 2 electrons in them. So 2s can have 1, 2, 3, 4, 5, 6, 7, 3. 2s can have 2, and 2p can have 2, 4, 6 electrons total. So when n is equal to 2, there are 8 possible electrons that can fill that shell. Then up here, we've got 3s, so n is equal to 3. Here we've got n equals 3 and L equals 1. Remember that that would be 3 possible values, M1. So this is all 3p orbitals. What comes after p? These are also n equals 3, but this time L equals 2. So these are the 3d orbitals. Remember, these are the ones with the weird combinations of like x squared, y squared, xy, etc. There are 5 different combinations for those. So in the n equals 3 energy level, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possible electrons. Then we've got 4s, um, 4p, and 4d. After 4d, we've got 4f. So remember here, we would have had L equals 2, or sorry, L equals 3. No, L equals 2. And then the next possibility, we've also got another possibility for L. So that's how we end up with the F orbitals here. Then, now we're going to see that these energy levels are really close together. Hard to know what's higher, 5s or 4d. Remember that electrons are always going to fill the lowest possible energy level first. And in reality, 5s is just a little bit lower than 4d. So 5s gets filled before 4d does. So 5s, 5p, 5d, 5f, and so on. Then we've got 6s, um, 6p, 6d, and 6f would be way up here somewhere. So you can see that sometimes as we get higher in the energy levels or higher in the orbitals, sometimes a lower or a higher value for n is actually lower in energy than some of the other orbitals. So pay attention to that. We'll come back. Hmm. So an atom's electron configuration is a shorthand notation that shows the number and arrangement of electrons in its orbitals. An atom's chemical properties are mainly associated with its ground state electron configuration. So that's why those Lewis dot diagrams and the Lewis diagrams that you learned in grade 10 and 11 are so useful. The ground state configuration is super important for the behavior of the atom. Here I've got the electron configuration written out for the first three elements. Hydrogen, N equals 1, L equals 0. 1s, and there's only one electron, so we put a little 1 there. Helium, 1s, but now there's 2 electrons for helium, so we put a little 2 there. Sometimes it might be useful to have a periodic table sitting right beside you as you do this. So you can think about how many electrons each atom has. So lithium, 1s2, it's got 2 electrons in the 1s orbital, and then 1 electron in the 2s orbital. It's something called the Aufbau principle that tells us that in the ground state of an atom or an ion, electrons fill orbitals of the lowest available energy level first before moving up to higher energy levels. 1s gets filled before 2s. 2p gets filled before 3s, and so on. If we're writing these electron configurations, we write them out like this: 1s2, 2s2, 2p1. Pause the video here and think for a second. What element would that represent in its ground state? Okay, so notice that there would be 1, 2, 3, 4, 5 electrons. So 5 electrons would be boron. This would be the ground state configuration for boron. An orbital diagram takes, instead of having this written out electron configuration, it uses little boxes to represent each orbital and the orientation of the electrons in that orbital. So an orbital diagram uses a box for each orbital in any given principal energy level. Empty boxes mean that there's no electrons there. Not that those orbitals don't exist, they're just not full. And we use a little arrow, or sometimes instead of an arrow, you'll see a box with a little half arrow. So that shows an orbital with a spin in one direction. An arrow pointing in the other direction shows an orbital with a spin in the opposite direction. if you've got two arrows, it shows that your orbital has two electrons in it. It's full. Also, sometimes you'll see them represented like this. So, um, spinning in two electrons, spinning in opposite directions. So, if you're drawing these orbital diagrams, there's some guidelines for how these orbitals get filled. We place electrons in the orbitals in order of increasing energy level. Each set of orbitals in the same energy level must be completely filled before you move on to the next orbital. When you add electrons to the orbital of the same energy sublevel, each orbital receives one electron before they get paired. This is super important to remember. And when electrons are added singly to separate orbitals of the same energy level, they all must have the same spin. Put together, number 3 and 4 are known as Hund's rule. So let me show you exactly what I mean. We're going to write electron configurations for periods 1 and okay. So for this next part, you're going to want to go back to the workspace and hopefully we can see this. If you open up the card here that says lesson 1.3.1, electron configurations 1, you'll see that there's a doc in there that looks like this. So this doc, you can either print it out or just do them on paper. But follow along and I'll show you how we complete these orbital diagrams for the electrons, or for each element and its number of electrons. So starting here with hydrogen. Hydrogen, we know, has one proton, and in its ground state, it has also one electron. So the first orbital that gets filled for hydrogen is 1s. There's only one electron, so that's it. So its name would be 1s1. The next element, take a look at your periodic table, it's helium. It's got two protons, so two electrons in its ground state. Now, I know I need to fill 1s before I move into 2s, but these two electrons can't be spinning in the same direction. They have to have opposite spin. So now I've got a full shell 1s2. Super full, super stable, noble gas. This makes sense. Um, it's hard to remove one of those electrons from helium. They're super close to the nucleus, they're spinning in opposite directions, the shell is full, it's stable. Now let's move on to lithium. Z equals 3. So lithium has 3 electrons in its stable ground state. 2 would go in the first orbital. Now this is full, and I need to put my next electron in the next orbital, the 2s orbital. So you can see again, if you think about it, why lithium so often has a positive charge. It's really easy to remove that one electron. It doesn't take very much energy because it's all by itself um, and in a higher energy level. So lithium's electron configuration would be 1s2, 2s1. Okay, let's move on. Next would be beryllium. 4 electrons. So we fill 1s and 2s before we put an electron into 2p. 1s2, 2s2. Give me a sec here. I gotta be able to scroll down. Oh, cool. It kind of stuck with where the text was. Okay. Um, After beryllium, we would have boron. Boron has 5 electrons. So 2 end up in 1s, 1s2, 2 end up in 2s, 2s2, and 1 in 2p. So 2p1. Okay, pause the video here and try and do carbon, nitrogen, and oxygen on your own. Okay, let's double check your work. So carbon would have 6 electrons. Now, this is interesting. Here's where you have to remember Hund's rule. Instead of pairing to fill this orbital first, what actually happens is the electron fills an empty orbital, spinning in the same direction as that first electron. So instead of pairing, you end up with 2 electrons spinning in the same direction in opposite p orbitals. Hopefully, you remembered that when you tried this on your own. Nitrogen with its 7. Again, I don't spin pair them first. Instead, I fill the separate orbitals first. Two p3. Then moving on to oxygen. Oxygen has 8 electrons. This is where you start spin pairing electrons in that p orbital. So now oxygen has 2 paired electrons and 2 lone electrons. Oh, that should not be a 3, that should be a 4. Okay, I hope you're starting to see the pattern here. Pause the video, take the time to complete this worksheet. Okay, I hope you actually did as I instructed. If you did, you noticed that by the end of this, it started to get very, very repetitive. And wouldn't it be handy to have a way not to rewrite that beginning 1s2, 2s2, 2p6 pattern again and again and again? It definitely would be. So if we're talking about an element like sodium, give me a sec. I seem to have forgotten how to use the pen again. Okay, if we're talking about an element like sodium, sodium has 11 electrons. Um, and if I was to write out the electron configuration for sodium in full, I would write out sodium 1s2, 2s2, 2p6, 3s1. Then, if I was thinking about magnesium, I would still have to write out 1s2, 2s2, 2p6, 3s2. This whole beginning part, that gets repeated again and again as you go further down the periodic table. So it's really useful to have a short form for that. Instead of rewriting the electron configuration for the whole beginning part, instead, we can just write the noble gas that comes before that element. So sodium is right after neon. So we write in square brackets neon and then 3s1. Magnesium is 2 uh, after neon. So we write in square brackets neon and then 3s2. It allows us to not write this part again and again and again. It's a good shorthand. I will make you do both the long form and the short form on task or on next task, but it's important to know that there is a short form to reduce the amount you have to write. Okay, so now make sure that you've completed that worksheet. And once you've got it done, write condensed electron configurations for all of these elements as well. Everything past helium can have a condensed electron configuration to go along with it. And this last slide just does a really good job showing you the differences between the energy levels. If we take a look at this, you can see very clearly that 3s is lower in energy than 3p. So electrons would fill 3s, then 3p. But 3D is higher in energy than 4s. So if you were starting to fill fill orbitals, you would need to fill 4s before you filled 3D because electrons will move to the lowest possible energy level first. Okay, important things to keep in mind. You can refer back to this if you need it while you're completing your worksheet and writing your condensed electron configurations. Okay, that's your goal for today. Hopefully, we'll see you tomorrow.